computer. We are recording. Okay. Admit all. Okay, I think we can get started. We are happy to have Raphael Zentner giving us the last talk of the spring Gauge Theory virtual seminar. We will take a break for the summer. We are talking about organizing a virtual summer Gauge Theory conference. We'll certainly post information about that on the website and the seminars list and the geometry listserv. I will turn off my video and mute and let Raphael take it away.
Okay, so yeah, thanks very much for inviting me to present this. Okay, so so this is going to be about character varieties, SU2 character varieties, and surgery obstructions, and it's joint work with Stephen Sivek. So okay, so the way I will set this up will be I will, I mean, just as an outline of the talk, I will speak about surgery obstructions and recall a few things that most of you probably already know. And then about SU2 cyclic or SU2 abelian 3-manifolds. And then there will be a main talk, then there will be a main result, which is that a certain class of 3-manifolds cannot be obtained by surgery on a knot in S3. And well, and then I'll give the proof. Okay, so let me get started. So the question is, when is Y a 3-manifold surgery on a knot in S3? And there are some obvious obstructions. One is that the first homology group must be cyclic. Another one is that pi1 of Y must be normal generated by one element. Okay, so this is just because we know that for the complement of a knot is normally generated by the meridian, and the 3-manifold we consider, I mean, surgery on a knot, is therefore a quotient of that group. Okay, and so this last condition of the fundamental group is also called weight 1. And in particular, like a 3 torus cannot be surgery on a knot in S3 for those reasons. So then there have been some more refined results to obstruct surgery, and I'll mention certainly not all of them, but one is due to Dave, which says that there is a weight 1 integral homology 3-sphere, which is not surgery on a knot in S3. And this uses instanton gauge theory on end periodic manifolds. Okay, so by the way I have set this up, so I'll scroll down on my tablet, but this is synchronized with some file in the Google Drive folder, and I share the link to this by the chat. So what you can do is you click on that link in the chat, and then in the browser a page will open, and from time to time this will update what I have written previously. So as I keep on going on that in that browser window, you can just scroll back and see what I have written before in case you want to do so. There is there are more obstructions due to Boyer lines. And these use the Kasson-Walker invariant. That is, I think, from the 90s. And then more recently, there is a result due to Jennifer Homm. I don't know how to pronounce his first name, and Ty Littman. And they proved that many Brieskorn homology spheres aren't surgery on a knot in S3. And this uses the D invariant in Heegert-Fleur homology. Okay, and so here comes something that seems probably totally unrelated. So let's start with the definition. Oh, okay, so David just, okay, I see. David just made a comment about whether he isn't sure that his have weight 1. Okay, I thought they had. Okay, but thanks for the update. I mean, certainly the ones due to Stephen Boyer and lines, they do have this property of being weight 1. Okay, so here's the definition. A 3-manifold M is SU2 cyclic if all or SU2 abelian if all representations rho from pi 1 of M into SU2 have cyclic image. respectively abelian image. And in fact, the two notions are the same for rational homology spheres. So I might just stick to saying SU2 cyclic. And why should one look at this? As a motivation, so such a three-manifold is simple from the point of view of instanton gauge theory. Okay, and they correspond somehow to the strong L spaces in Heegard-Fleur homology, introduced, I think, by Josh, although not under, not with this name, making reference to Francesco Lin's talk to three manifolds with no irreducible solutions to the subargredin equations. Okay, so yeah, by the way, I should say, I mean, I can't state the main result yet, but in the end, the result will be a class of three manifolds which satisfy the weight one condition on the fundamental group. And our result says that these cannot be surgery on a knot in S3. So they somehow fit into these classes of results, which by far aren't complete. But in a sense, the methods that we use for the proof are far less advanced in a sense. I mean, far less, I wouldn't say. Let's say it's methods that won't use gauge theory, really. So also apologies in this sense, since the proof of the main result will not use gauge theory, really. And this is a gauge theory seminar. So I should share again. Oh, there's something going on in the chat. So I can't just look at the chat all the time. So what you should do is, if there is a question that that is asked, that is being asked to me, just shout, just tell me.
Don't worry about it. We're just talking amongst ourselves.
Okay, that's fine. Yeah. Okay, so and then here's a question. Oops. Oh, it's actually a Kirby problem. If y is a integral homology.
Raphael?
Yes?
There was one request that was addressed to you, which is there any way to make your the screen share part of your
oh, larger?
Larger? Yeah, it's a little hard to read.
Oh, I see. So I was told how to do this. So apparently you have some options and you can scale it.
Oh, so we can do that on our own screens. Okay.
So you can do that on your own somehow, but I can't do it for you.
Yeah, I think there's still something funny because it's scaled as much as possible. Anyway, we'll sort it out. Don't worry about it.
Yeah, you should better figure that out. So can someone explain to the others how to do it?
It's different on every device. On the iPad, it's working very well just with two fingers.
Yeah. Anyway, okay. Don't worry about it.
Yeah. Okay. Yeah, but thanks for addressing this.
We can open the document and rescale with some delay, I guess.
Yeah, okay, but then you don't see my writing in real time, right? Okay, yeah. So Danny, tell me if the problem persists, please.
Yeah, it's still there. But it's not. We'll survive. Don't worry.
So there's some options to click somewhere on the top of the screen, usually on the right. It's not there on my screen right now.
Yeah. So. Okay. Yeah. Actually, mine it says View Options, and then you click 100% original size. So yes, actually, that does solve it.
Okay, okay, great, great. Yeah, okay, thanks. Yeah. Okay, so here's the problem. So if Y is an integral homology 3-sphere and Y is different from S3, is there an irreducible representation of the fundamental group of Y in SU2? And so there's a strong evidence for a yes answer. And I'll just give a list, which probably also won't be complete, but yes, if Y is a Seifert-Fibert integral homology 3-sphere, and that I think was first studied by Fintuschel and Stern in the 80s. Then yes, if the Rochlin invariant is non-zero, and that was proved by Cassen in the 80s. Let me get this a bit. So this is meant to be a row. Okay. And this reduces the Cassen invariant and the fact that the Cassen invariant reduces to the Rochlin invariant modulo 2. Yes, if Y is obtained by surgery on a knot, on a non-trivial knot. And that is due to Kronheimer-Mrvka from 2003. Yes, if Y has a Stein filling, or is the boundary for Stein domain, that is due to John and Stephen from 16. And it's yes, if Y is a splicing of two non-trivial knots. In S3. So that is Y is the exterior of a knot K in S3 glued to the exterior of a knot K prime, such that the meridian of K is glued to the longitude of K prime, and the longitude of K is glued to the meridian of K prime. So that gluing, that particular gluing, it's maybe not what people understand by splicing in the most general case, but this particular gluing gives an integral homology sphere. So that's due to me in 2016. And then the answer is yes, if Y is toroidal. And that is due to Ty Littman, Juanita Pinson Caicedo, and me from last year. Okay, so that's about it. Well, I guess, I mean, that's most of what I know about it. And yes, we don't know the answer in general, and in particular, it seems hard for hyperbolic integral homology spheres in general. And yes, so by the way, the answer to this question is yes, if we replace SU2 by SL2C, and that's also a result that I proved in 2016, which actually uses this splicing result. Okay, so now what if you ask the same question for rational homology spheres instead of integral homology spheres? So same question. for rational homology 3 spheres instead of integral homology 3 spheres. Well, so it's obviously no for length spaces, since they have a cyclic fundamental group. Oh yeah, so let me also say that like the last 3 results, 3 or 4 results here have been also proved with instanton gauge theory. Okay, so yes, if Y is surgery on a knot in S3, if the slope of the surgery is bounded above by 2, and that is also due to Kronheim and Rufka in 2003. Yes, if Y, oh, so this is again, K is a non-trivial knot here. If Y is S3 is surgery on a knot with a big enough slope. So these here are non-trivial knots. I'll just post that link from time to time again, since there might be people showing up late. So this is due to Stephen and myself from 2017. Then it's no for the 37/2 surgery on the -237 pretzel knot. And that is due to Dunfield. So I think he found this initially numerically, but then verified like rigorously. So notice also that 37/2 is just in the middle between 18 and 19, and 18 and 19 are both length space surgery slopes for this knot, for this pretzel knot. So here's a large example that will play an essential role later in the talk. So no for Motegi's examples. And these are, I'll denote them by YAB, CD. These are going to be the exterior of a torus knot AB glued together with the exterior of a torus knot CD, such that the meridian of the first one goes to the Seifert fiber of the second, and vice versa. So this the Seifert fiber is really different from the longitude. So this gluing is, so this is a rational homology sphere, but not never an integral homology sphere. So this has order of H1 equal to A, B, C, D minus 1. And so here are 2 more examples. Yes, for surgery on a non-trivial knot, and that is due to John and Stephen from last year. And then no for the branch double cover of the knot 818, and also the branch double cover of the knot 10-109. And these are both hyperbolic examples. And so, by the way, if you use Snappy and Snappy inside Sage, you can. I mean, Nathan Dunfield has written a program to test. I mean, which is numerical, but to test for SU2 representations. And so in the census manifolds that Snappy has inside. There are very few hyperbolic examples of SU2 cyclic manifolds, but there are quite a few. I don't quite remember. There must be at least something like 30 or 50 which have even order of the first homology, and of odd order, I think there are far less. There are these two and the third guy, which right now I just don't remember. Okay, so so let me see. Yeah, I think you should see how the proof works for the Motegi examples. Just to give you an idea, proof of SU2 cyclicness of Motegi's examples. So let's write Y as a, Y1 glued together with Y2, and then if we have a representation rho from pi1 of Y to SU2, we denote by rho1, rho2 restrictions to pi1 of Y1 or pi1 of Y2. So so first of all, what you can see is if both representations rho1 and rho2 have a abelian image in SU2, then the thing that you glue together will again be abelian. So at least one of them has to be non-abelian or irreducible. So suppose rho1 has non-abelian image. So that means that, in fact, the Seifert fiber in a Seifert fiber space is in the center of the fundamental group, so it commutes with all other elements. So if there's a representation with non-abelian image, then it has to map the Seifert fiber into the center. Okay, so that means rho2 of the meridian on the other side lies in the center. But the meridian normally generates the fundamental group of the other guy. So that means rho2 of the second Seifert fiber is also mapped into the center, but that is glued to the meridian of the first guy. So that is has image in the center, and so the representation on the first I mean on Y1 has already been trivial or central. Okay, so here's the let's say here's the main theorem, and I state it in a way that is somehow easy to state. It's not certainly not the most general result. So I write sample statements. So if A and B are integers bigger than 2, then that Motegi manifold AB, let me write, to remind you that this depends on torus knots, let me write it this way. then this manifold is not den surgery on any not K in S3 for a density 1 subset of numbers A times B in N. By the way, so yeah, so the prime numbers certainly are of density 0. So density 1, so a set is of a subset of N is of density 1 if you take that set, you intersect it with the numbers from 1 to N, you divide by N, and the limit of this is equal to 1. So that means density 1, and then correspondingly you can define that for fractions. And so main theorem 1 prime is the following. Similar, just as, yeah, essentially the same statement, but for y of TAB. And so, so here's a remark. So some of these Mortiggi manifolds actually are arise as surgery or knots in S3. So let me tell you about this. So there's this class.
Raphael, could I ask quickly, was there a condition on C and D in main theorem 1? I'm not seeing why it doesn't just
on A, B? No, you mean what?
On C and D.
On A and B?
On close. On C and D.
Oh, I see. Oh, thank you. That was Josh, right? Who asked the question?
That's right. That was Josh.
Yeah. Thanks a lot. It's yeah. It's minus A, B. Yeah. Okay. Thanks a lot.
Yeah, cool.
So similar statement where this product here is all positive. Okay. So why is this important? It's that this class for some for any integers L and M, maybe except of, I don't know, -1, 0, 1 or some trivial small cases, but for all but certainly for all but finitely many, these are half integral surgeries on Ödave-Munoz knots. Okay, so there's no point in drawing these knots, but I will say something about them. These are hyperbolic knots. They're actually all fibered, and they have some properties respect to surgeries. So these are all hyperbolic, and yeah, they'll appear later in the talk. So in particular, the ones of these Mortiggi manifolds you get, they all have A, B, C, D smaller than 0. And in particular, so why I stated this as main theorem 1 and 1 prime. So there seems to be a bit of a divide into whether the product of all these numbers, with these I mean all the product of all the 4 that appear here, whether that is negative or positive. So here the product is positive, and we conjecture that in this case you can never get it as a surgery on a knot in S3. Wait, yeah, I think that's really formulated that this way in our paper. And then also in the case where the product is negative, also most cases cannot arise as surgeries or knots in S3. Okay, so so now so that was the introduction. So proof of the main theorems. And really there's no gauge theory there. So I hope that's not too disappointing. So the proof deals separately with the possibility of these manifolds being integral surgeries and non-integral surgeries. So let's first have a look at integral surgeries. And then we have the following proposition. If minus A times B, oh sorry, not minus. If A times B and C times D are not squares modulo the order of the first homology group, which is A, B, C, D minus 1. Then Y, A, B, C, D, that multi manifold is not minus A, B, C, D minus 1 surgery on any node in S3. And now there's just a similar statement for, oops, there's no minus here. Okay, so, and then there's, so yes, so we know if it is integral surgery, then certainly surgery slope is either A, B, C, D minus 1 or its inverse. And yeah, so the inverse is dealt with the following case. If minus AB and minus CD are not squares modulo this number, then this manifold is not negative ABCD minus 1 surgery on a knot in S3. And the proof of this is rather elementary. It uses the linking form. So proof uses linking form. And you do the following computations. So for the Motegi manifolds, we do have these meridians of the knot, the torus knot AB, and this is minus CD divided by ABCD minus 1. And on the other hand, if Y is N surgery on a knot K, then you compute that Ly of mu K is equal to minus 1 over N. And here mu K generates the first homology group of the surgery. And so that linking form is so this takes value in the rationals modulo the integers. And now so if the Motegi manifold is given by surgery on an integral surgery on a knot K, then mu AB is some multiple of mu K in homology. And so therefore, what we get here is that this is x times mu K, x times mu K. And so then you see by this that oops, that you have minus x squared divided by a, b, c, d. That's what you get from the second computation, that this is congruent to minus cd divided by a, b, c, d minus 1 modulo 1. And that is equivalent to saying that x squared is c times d modulo a, b, c, d minus 1. And so that is the statement in the proposition. So in particular, a times b, so we have just proved that c times d has to be a square modulo a, b, c, d. And then you do the same thing with the role of, instead of you take mu ab, you take mu cd, the other meridian, and that gives the other condition. And the same then holds if you for the orientations reversed, except that, sorry, not orientations reversed, but for the negative surgery, the only thing is that then this sign will change. Okay, so that deals with integral surgery, so I shouldn't have spent that much time on that. But so it is clear that from this proposition, just arithmetically, you can rule out the possibilities that the Motegi manifold is surgery, integral surgery on a knot in S3 by putting up the numbers A, B, and C, D, and so that that they don't occur as squares. Modulo A, B, C, D minus 1. So that's just purely arithmetic, and this is where the density result comes from. Okay, and then one has to deal with the non-integral case, and that is that for this we can make the following statement. If a Motegi manifold is non-integral surgery on a knot in S3, then K is a Oedave-Munoz knot. So by the way, Oedave-Munoz, it's one person. And R is the unique half integral. Yeah, so these Oedave-Munoz knots, they are particular in the sense that they have surgeries which are toroidal. So I mean, by Thurston's hyperbolic Dehn surgery theorem, I mean, for all but finitely many surgeries on a hyperbolic knot, you get a hyperbolic manifold. So this is atoroidal, but there are some exceptions, and these Oedave-Munoz knots, they do have they have such exceptions. Half integral toroidal surgery slope. And these Motegi manifolds, of course, they are toroidal because they have this splitting torus that splits the two knot exteriors into two. Okay, so and then for the proof, well, we treat the different cases. Treat the cases that K is a torus knot, that K is a satellite knot, and that K is hyperbolic. So any knot in S3 is one of the three. So first, let's deal with the torus case, which is the simplest one. No surgery on a torus knot is toroidal. In fact, these had been classified by Moser, forgot her first name. But in any case, the surgeries that the surgeries that on torus knots that occur are either Seifert fibered with 3 singular fibers, or a lens space. And actually, there are infinitely many cases where lens space occurs, or the connected sum of a lens space with another lens space. So these are well understood, and these the Seifert fibered 3 manifolds with at most 3 exceptional fibers, they have no essential surfaces. So they are simple. They, in particular, they're not toroidal. Okay, so the hyperbolic case is quite interesting, and it's sort of you know, so I think historically interesting also. So the conclusion follows from the following fictitious dialogue. That could have happened, and somehow it did happen. What Gordon and Lücki have proved is the following. If K is a hyperbolic knot, in S3, and surgery on this knot is toroidal, then Q is at most, the denominator is at most 2. So it's at the worst half integral. And there were many integral cases known, but I think not so many half integral cases. So, and I guess implicitly they asked about cases with Q equal to 2. And then Udave Munoz gave an answer. So he constructed infinitely many hyperbolic knots with half integral toroidal surgeries. Okay, so and then Gordon and Lücki had actually realized that this is all that he actually gave. He just found not just some examples; he just found all of them. So Udave Munoz has found all examples. Okay, so, well, I guess in a sense it was a dialogue. And so, you know, I mean, there's this machinery of graphs of intersections of essential surfaces and all their combinatorics. So this is what Gordon and Lücki have done a lot and proved great things for that. I mean, I've never gone that much into it to understand it, so it remains quite mysterious to me. But I asked Gordon once about it, and for him, Udave Munoz as a result was just pretty mysterious. He just, I mean, it's sort of, for him, it was incredible that he just, you know, he just comes up with all that can possibly exist. It's a very large class of knots, by the way. Okay, so we're left with the satellite case. And we, oh yeah, so by the way, so why does this deal with why does this prove our theorem for the case that that K is a hyperbolic knot? Well, because yeah, I mean, well, yeah, it just, I mean, okay, yeah, no, that is just this statement, and it's a strict subset of the possible Mortegi manifolds. So this is why, yeah, why the main theorem will follow from this and the linking form obstruction. Okay, so so here we'll use the following little lemma, which is that the splitting torus in the Mortegi manifold is the unique closed incompressible surface up to isotropy. Well, so you prove this just by you take the minimal number of intersections with that splitting torus, and well, if the surface is essential, then the corresponding slopes are boundary slopes for the knots. And for torus knots, we know what they are, and they're just the longitude slope and the Seifert fiber slope, which bounds an annulus. Okay, so okay, so so we'll deal with this situation. K is P of L, where P is the pattern, and L is called the companion. So, well, so let me draw an example. So here the companion is the figure 8 knot. Well, it should be, and the pattern is the Whitehead pattern. Okay, so slightly more schematically, the exterior of the knot K is given by the exterior of the knot L. Then here there is the satellite torus. And it's the boundary of this torus in which you have drawn the pattern, and then you have tied the solid torus. So here we have a solid torus without a neighborhood of the pattern. And then this is the boundary torus. And if we take surgery, then we just add this, add a solid torus here. Okay, so now here we have to consider a few cases. So the first case is so let's call that satellite torus T. The satellite torus T stays. Well, so we're assuming that our Mortegi manifold is non-integral surgery on a knot K, And well, then we can ask what happens with the satellite torus, and it can either compress or stay incompressible. And in this case, the lemma implies that T is equal to the splitting torus, which separates the two torus knot complement, the torus knot exteriors. Okay, so what does that mean? This means that this surgery where we have E of L here we have S1 times D2 minus the neighborhood of the pattern, and here we have S1 times D2. So if that is the splitting torus of the torus of the Motegi manifold, then this side has to be Seifert fibered, and also the right hand side has to be Seifert fibered. Okay. So that means L is a torus knot, and the other side is and right hand side is Seifert fibered also. So the right hand side is really surgery on a on the pattern, but inside the solid torus. So that's a bit different of what, you know, it's not in S3, it's not in a solid torus. And there's a result of Miyazaki Motegi, which have studied such knots. And it says that P, the pattern, is a cable of a zero bridge braid. And so this is because the surgery slope infinity and surgery slope is not integral. These cases do not occur. And well, in this case, actually, you can see the two exceptional fibers that appear here. So it's one is from I mean, so it's a cable. Okay, so what is a zero bridge braid? A zero bridge braid is really a torus knot that you draw on the boundary of a torus, and you push it slightly in, and it's a cable of this. And so you see that there is a Seifert fibration, which is once the core of the solid torus, and then another one which is the core of the cabling torus. So there are two there. And that means that K is a second iterated cable of a torus knot. And however, we have the following sort of classification result, which actually does look at SU2 cyclic surgeries on iterated torus knots. So SU2 cyclic surgeries on iterated torus knots are length spaces or length spaces connected some RP3. And none of these are toroidal. So that cannot happen either. And then finally, there's the case left of that the satellite knot compresses. Sorry, the satellite torus compresses. And yeah, I'm running out of time. So I'll just mention that this uses results of Color, Gordon, Lücke, and Shalen, and some results of Gordon about surgery on cable knots, surgeries on cables of knots. Okay, I guess my time is over and I should stop here.
People can pitch in questions. If people don't have questions, we could take a couple more minutes to finish 3.2 for those who are interested.
Okay, yeah, thanks for coming from so many places.
Thanks for the talk, Raphael. Enjoyed it very much.
Yeah, okay, great, thanks, yeah.
Okay, maybe I have a question. Hi, Raphael. So your methods are for rational homology spheres, right? Could they say anything about integral homology spheres? Or?
I guess they could say something, but you'd have to come up with possible examples. I mean, I guess the main trick here is this result due to Gordon and Lücki, which classifies the half integral toroidal surgeries on hyperbolic knots. Yeah, I mean, it's a, well, I guess, well, I guess it could possibly work, but yeah, I mean, well, in a sense, no, because, I mean, we really use these results of SU2 cyclic, I mean, so our methods really relied on the fact that we understood SU2 cyclic 3 manifolds for large classes. Like one of it was I mean, actually small, I mean, all Seifert fibered manifolds, but also these surgeries on iterated torus knots. And for integral homology spheres, I mean, I guess the conjecture is that there are no SU2 cyclic examples. So yeah, it wouldn't quite work that way, but it is certainly possible that this classical methods using also color Shalen theory and these, you know, Gordon Lücki machinery, I guess it is possible that this says something about the possibility of a 3 manifold being surgery on a knot.
That would be interesting. Thanks.
Stephen, what would you have to say about that?
Well, I think the main thing I would have to say is that you proved that there are no SU2 cyclic toroidal homology spheres. So, you know, all the stuff that uses toroidal manifolds won't apply to integer homology spheres.
Yeah,
which is too bad. But, you know, maybe just one extra thought is that, you know, all this is about SU2 cyclic because it's sort of easy to understand the character variety in that case. And if the SU2 character variety were just a little bit more complicated, there were, you know, very few conjugacy classes of irreducibles, for example, you could probably work a little harder and still get similar obstructions. We just haven't actually done that.
It's also, I mean, in a way, you know, we weren't looking for these obstructions specifically. I mean, we were interested in SU2 cyclic 3 manifolds and somehow then found that result. But, you know, I guess if you had given that problem to a person like Gordon, you know, I assume that he may have just done it explicitly without ever referring to SU2 cyclic surgeries or SU2 cyclic manifolds. But you know, you'd have to understand possible surgeries on, you know, large classes of knots really well. So.
Hi, Raphael.
Hi.
I have a question.
Oh,
So
hi, Chris.
If you just change the question to, is your 3-manifold surgery on a 2-component link, for example?
Yeah, the answer is yes, it is.
All of these Motegi?
Yeah. All of these Motegi manifolds are surgeries on 2-component links in S3. Yeah, there's an argument in our paper.
Great, thanks.
Yeah.
Well, I should thank everybody for participating again. This will be the last one for this spring. We're debating about putting together a virtual workshop for the middle of the summer, and then periodically repeating this in the fall and when COVID's not down, but certainly not every week once we are back to normal.
Okay, Dave, may I also make an announcement? So in Regensburg, we are also organizing a low-dimensional topology seminar at the moment, and it will run until the end of July. You can find a link on my webpage. And you know, I guess some of you might find that also interesting. It's at 4 p.m. our time, which would be at 10 a.m. your time, and is at on Tuesdays. So just feel free to come. Okay, so
thanks, Raphael.
Yeah, thanks. Yeah.